Okay, so hello everyone. I think it's the time to start the lecture. And for the next two lectures, I will be giving the course on one particular topic that, well, is connected to machine learning, but that is also, well, a bit in the statistics and, well, let's say track. It's not all machine learning, but there's a lot machine learning involved. Right. So mm, let's start the following way. Let me first find the slides. Okay, exactly. So as you see, the um, lecture is called The Inverse Problem in Science. And there, what I want to do is to introduce to you one particular way to perform statistical inference. And this is an implicit likelihood method that is very much based on machine learning to work. So I think we will do the lecture as follows. As usual, you have like the long break in between. So we take this 30 minutes break after, well, let's see when I think it's fine, but let's say in 90 minutes or so, depending on that. And of course, since this is fully remote, you can ask questions on Zoom. I don't know what's the best way to signal questions. Probably raising your hands or directly speaking is probably one way to do it. Right. So, the problem is I have here my Mac iPad, and this is always echoing, and I have no idea how to turn off the the voice. Okay, I will do it like this for the moment, and I will turn it on when I need it. Okay. Okay, so as I said, this is about machine learning, but also statistics. But the actual question is, why do we talk about statistics at all in a machine learning course, and in particular here, Bayesian statistics? And this has to do with the following fact, and this is a very simple fact, which is simply, well, why do you use machine learning in your life as a researcher in the first place? And you could use machine learning in a sense that you certainly have discovered in the past lectures, and this is to use machine learning as a way to, well, interpolate your data and to produce a way to detect certain features in your data, to compress your data, all of that. But there's another way, and this is to use machine learning directly for performing the inverse problem in science. And physics, biology, chemistry, neuroscience, they all are observational parts of the science, meaning that what we are trying to do is to explain nature by having some theoretical framework, if you wish, a model that predicts what we observe. And observations are the key to progress in said physical sciences. Now, of course, also observations give you an incentive to form a certain model, of course, and to develop a theory from what you are observing. But then, of course, how do you get from the observations back to your model in terms of informing yourself about what your model should predict and what your observation actually tells you about the validity of your model? Well, for this, you observe and you obtain data, and then you have to go through the third step here, and this is the inference, which typically involves some statistical framework that you apply to your data in order to get some information about your model that you put in there in the first place, and that is your current system of belief. Now, doing this will give you a certain prediction for the model or a conclusion whether or not this model is true. Exactly this part here from the inference using data to the model is called the inverse problem. So you just don't make a forward modeling as it's just predicting what your model tells you your observation should look like, because this is not really how science works. We are not living in a theoretical world where the model is the truth and reality has to follow. It's rather the opposite. We observe and we try to find a model that actually explains reality. And so we need this inference part to actually know something about that and to inform our model. For lab experiments, this type of inference is not that complicated in a sense that there you can, even on a table, install your experiment. If it's, for example, an experiment with lasers or in a laboratory with chemistry or biological tissues, there you can just set it up and kind of control the systematic uncertainties that go in your experimental design. And you can repeat this experiment, well, depending on whether or not you have the materials, many, many times. Fine. But if you go to other places where also science is applied, like cosmology and astrophysics, there it's a bit different. There, we only observe one universe and we only have one universe, and all its physics it contains that we know and we do not know. So, whenever you measure something, you will measure parts that you know, and there could be parts that you actually have no idea exist and are still in the data. So, you have not really a control over your full systematic uncertainties in the problem. And we have to deal with that when we want to infer something from this data. So there are problems associated with both astrophysics and this only one universe and lab experiments controlling your systematic uncertainties. Well, now for machine learning. What machine learning does in principle is it is a glorified fitting machine. So it's a very expressive tool that can learn from input and gives you some output. And as I said, when it learns that from the input, it can even reach great accuracy. By default, however, machine learning algorithms and neural networks, when you train them, they do not really have a quantification of what the uncertainty is in that prediction. Fine. While for science, as I said, what we do is, well, we are interested in the parameters that explain data. So we do observations, and what we actually want to know is how confident are we that our model is true? Are our observations actually falsifying the model we are currently applying and have as the best explanation of that observation in mind or not? So, well, what's here the connection? Well, exactly that comes now in play when we do inference. So we do not simply want a best fit, we also want an uncertainty estimate of a said fit that may or may not depend on our prior beliefs in what should be the true answer to the problem. And the idea here is to merge machine learning with Bayesian statistics. So we want to solve the inverse problem with Bayes' theorem. Bayes' theorem is one particular way of doing statistics, and this comes more with the human intuition of what we learn by multiple observations of a certain event. So this is the general formula for Bayes' theorem, and we'll come to this later. But the idea is that in Bayesian statistics, you have a prior belief in your model and the parameters that this model may attain or not. With this prior belief, you can simulate data from your model that, well, should look like your observation. So let's say your observation is you want to model the different types of dogs that exist on the planet, so different dog races. Now, this produces you a certain underlying ground truth that your model predicts, and the model might have certain parameters, theta here. And then, given one particular observation, like this chihuahua here, you want to know, well, what is the parameter of my model from the initial prior that would predict me this shape of a dog? This gives you a so-called posterior for the parameters of your model that would be most likely to produce said observation that you had. However, what can happen in reality is that this likelihood of, given the parameters and how, given those parameters, my model or observation should look like, can be complicated to formulate. What you would like to have is something that is analytic and easy to evaluate, but sometimes you can't even write down what this likelihood should be. And in such a case, machine learning can be helpful to solve the problem. Because instead of trying to figure out what the likelihood is in analytic forms, you simply put here as a step a neural network that then implicitly learns what the likelihood is if you train it on the data that your simulation or model can produce from the parameters. So by just showing the network this training data set and saying this is connected to this and that parameter, it can, due to the expressiveness of neural networks, technically learn how this likelihood looks like, and then you can still perform this inference step of showing an actual observation and then getting something from this. And this is, in principle, the topic I want to talk about in those two lectures called simulation-based inference or implicit likelihood inference, which is probably a better name because whenever we do observations and we have a model, we technically always simulate something. So everything what we do is simulation based in some sense. So implicit likelihood is a better name for it because we learn implicitly a likelihood in this way. And this is how this will connect to machine learning and also connect to what you've heard before because many topics pop up again here. Okay. So what I want to do today in the lecture is introduce to you Bayesian statistics and some methods that come up there, then talk about one precursor of the modern implicit likelihood approach that is called approximate Bayesian computation, which is, well, has been put forward in the 80s. Then go a bit about the mathematical foundations about the simulation-based inference approach and its flavors because you can do this in different types, and depending on this, there will be different, well, ways you have to implement this. Well, next week, this will go a bit more in detail about some autoregressive models, some applications to physics, and how you validate that your method produces the correct inference. Okay, right. First, we should talk about Bayesian statistics and just set the general language for this particular two lectures and the method we will use. I was talking here again about the inference problem in science and solving the inverse problem to obtain information about your model from observations. So this is either in a forward way, if you have a model, depending on parameters, you can simulate whatever you would observe, or you solve the inverse given the target observation. What are the plausible parameters of your model? One is straightforward, the other is not, and we need the statistical inference to get, in this setup, a posterior for our parameters given the target observation. Well, this depends on the different quantities that pop up in Bayesian statistics. So from probability theory, there are some terms that one should recall here, namely the marginal of a probability distribution, which is basically the integrated joint probability density. So what we see here in the center is called a joint probability. Why is it joint? Because it is the joint probability density distribution of all variables in your problem. And in this notation, there's always a distinction between x being observation or some data, and theta being the parameter of a model. And of course, the joint probability is the probability of all that goes into your model, which is data and parameters. Of course, you can integrate out in this way the dependence on the observation or data, and then you get the marginal probability density of your parameters from a joint probability density. You can also have a conditional probability density by saying, okay, if I know that my parameters of this particular model are like this, then I know that the output probability of having this and this observation is, well, or will get a different value because you already have fixed a certain set of parameters. This can be expressed, for example, in this way, as the joint probability divided by the marginal probability of all the parameters. Basically saying that you divide by the overall probability only depending on your parameters from your joint probability. Right. And then this kind of conditioning can be applied in a chain rule to write your joint probability as the product over many of those conditional probabilities, as is indicated here in this particular formula. So there's always the way to, let's say, autoregressively describe your joint probability as the product of many conditional probabilities. We will talk about this in the next lecture, and this will also play a role in later lectures that then target transformers and how other machine learning approaches work. A special case of this chain rule is Bayes' theorem that we already have seen in one of the slides before. And this is the general rule that we will have to follow in these lectures. So the quantity here on the left-hand side of the equation is called the likelihood of the data. And this is if I condition my joint probability on the parameters. So the question here is, given the parameters, whatever they might be, what is then the probability of my observations to look this and that? The two probabilities here in the numerator are the posterior distribution. So this is given the data that I've seen, what is the probability of my parameter being this or that? So this is the property or quantity we would like to infer in the inverse problem. The quantity p of x is the marginal if I integrate out all the parameter dependence of my joint probability distribution. What is this? Well, this is called the evidence. This is the evidence of the data. So basically, this is a model-dependent statement that tells me how likely is it to get this type of observation or data point in the first place if I disregard or just integrate out the dependence on my parameters. So this is basically a measure of how likely a certain event is in general, given your model. And this P of theta is also marginal, but this is what we have previously called the prior. So this is the prior belief in your parameters. So in principle, what you can, of course, do is you can restore the joint probability density by, well, just switching the role in this equation here. So you can get the joint probability distribution by multiplying the prior of your parameters, which you can set because you know them. It's your prior belief, and multiplying this by the likelihood function. If you know the likelihood function of your problem because you can analytically write it down, you can simply form a joint likelihood. Otherwise, you have to know the joint likelihood and then do it the other way around. Okay. Right. I just want to have a brief touch on Bayesian versus frequentist view. So what we'll do here is the Bayesian view in statistics. Of course, you also have the frequentist approach to statistics, which will eventually arrive at the same result if the parameters are, or well, your prior input in the Bayesian way is put correctly. But it's a different way of looking at statistics. Well, so as I say, what we are interested in is a certain quantity, and this is how confident are we that the parameters we have inferred with our observations are correct. You would measure this in a certain failure rate alpha. So how many times are actually wrong if I say with my inference method that the obtained parameters are correct or not? So in a frequentist way, you would express this as a confidence interval at the level of 1 minus alpha. And alpha is this failure rate. So let's say if alpha is 5%, then you're 5% wrong, and your confidence interval is 95%. So 95% of the cases, you should be right. What does this mean? Well, for a frequentist, this means that the parameters of that particular experiment are fixed anyway. The only thing I can do is repeat different realizations of this because I have this tabletop experiment and I can just repeat everything over and over again. And this gives me different parameters, estimates. But I want that if I, well, average out, and this is this notation here, so this E is called the expectation value. And this is performed over different realizations. And these realizations are drawn from a likelihood. Because in the frequentist view, I know my likelihood of an event occurring given certain parameters. So I can repeat this over and over again. And I average out this quantity here, which is just saying, okay, the parameter I have obtained from my different realization is within a certain 95% rate around the true value. And what is the average value of that? Fine. For a Bayesian statistician, this is a bit different. So here we do not repeat experiments, we only observe once, but we can sample different parameters. We can sample different parameters, and what we can do is we can cross-check whether the particular observation that I had and the posterior that I obtained by looking at this observation, so here is again the posterior given a certain target, would produce the correct expectation. So if I do this for many steps and I have this certain, well, interval in my posterior that contains 95% of the interval where my parameter is supposed to land. Is this true? If I now sample many times from this posterior. Well, this is kind of a hard problem to solve for a Bayesian statistician because it requires you to sample a lot of times on the posterior, and this can be expensive. So also there, machine learning can help. So basically, the difference between these two points of view is a frequentist thinks about statistics in the sense of repeated experiments, and you obtain a certain parameter from that. While the Bayesian statistician thinks about it in a sense that you have an observation, and this gives you a certain estimate of a range of parameters that might describe that observation. And you can sample from your posterior belief in the parameter. So there is this difference in thinking. Okay. So before we dive back into this, let's have the recap of Bayes' theorem. That will be important for what we are doing here. So In the Bayesian inference, we treat everything as random variables, and we quantify the uncertainty in those probability distributions. In particular, a prior distribution for your parameters, given here in this formula as P of theta, or as a posterior. If you have seen a certain data set, you have a posterior belief in your parameters, which is then that distribution. You have a likelihood that is, given the parameters of your model, what is the likelihood of an observation looking like this and that. And you have here in the denominator the evidence of your data. Once you integrate out the dependence of your parameters, your model will tell you that is the overall probability of my observation to look like this. All right. So, and just to make this a bit more clear, let me make this visualization. And what I show here in the central part of this plot is the joint probability. And what it basically is the joint probability here is the joint probability of a one-dimensional problem. You have some quantity that is just distributed as a Gaussian, and you have parameters with a prior that also go as a Gaussian. And they are kind of correlated in a certain way. And this is expressed here in this tilted two-dimensional Gaussian as your joint probability. And now we can trace what the individual components are doing. So, as I said, if you want the evidence, you need to integrate out the dependence on the parameters of your joint posterior. So what you do is, as the prior or the parameter dependence is plotted here on the y-axis, you have to integrate your joint probability along the y-axis, but you keep the dependence on the x-axis, which is the probability of your data having this or that value. So if you do this and you integrate this in the y direction, you get this projection on the x-axis, which shows you, well, a certain type of Gaussian. And this black cross here shows you some target observation, let's say. Some observation that has been made with a certain parameter theta 0 and an observation x 0. Okay, and this lands exactly here. So it is within the bulk of the evidence. For the prior, this is the other marginal distribution. You do the opposite. You integrate out your x-axis, and then you keep the dependence here. And this will, of course, also give you a Gaussian, because both processes are a Gaussian. All right, and you see this here. Now, what is the likelihood? Well, the likelihood you get once you fix a certain parameter to a value, and then you trace along this fixed parameter, what is the probability density of my parameter that is left? This is here x, so the probability of having this observation x at a certain value. This would produce you this interesting looking shape, which is basically just a linear function in two-dimensional space. But if you slice this at each value of y, so the parameter value, you get a Gaussian. So each slice here is actually a Gaussian. And in order to get a probability density, of course, you have to renormalize, meaning that on all values here in the y direction, you have a distribution that is normalized to 1. This is why they all have the same color, if you follow this line. And the same is the posterior, but here you slice in the other direction and you fix the value of x, and then you go along here and trace what is the probability along now the y-axis. You renormalize so that for each fixed x, this probability density will integrate to 1 if you go for the full range, and then you get this particular shape. And this is, at least in this two-dimensional case, how you can think about these properties. So this joint probability connects all of these particular objects, and you can derive all of them. Okay. Mm, right. Just one word about how you perform computationally this Bayesian inference and what methods there are. This is just as an overview. So there are different methods you can use, and what is typically used in a great bulk of the literature is so-called Monte Carlo Markov chains. So there you would basically sample your likelihood function and you would try to chart the space of your likelihood function. Because as you see here, this method is based on exactly the likelihood and only the likelihood. Then you have another method that is called nested sampling. It's not so important what it does, but just that you know the name exists. This is a different way of doing the sampling of the likelihood function, which is not starting from one particular runner in your likelihood, but that induces or introduces many initial points of your likelihood function and then moves around in that space, which is more flexible and you can capture different kind of pathological behaviors of a likelihood function in a different way. Then you have something called Hamilton Monte Carlo, which is the gold standard for likelihood methods, because there you introduce more information to your problem, because you introduce a score that guides your Monte Carlo method. So there's one point that runs in the likelihood function with the derivative of the log of your likelihood function, which is a very designed problem to solve a very specific inference task for a very specific setup. So if you can write such a thing down, always use that because it will be the best thing you can do. And then there's something called variational inference, which we'll touch upon briefly also in the lecture. They come later. And then the simulation-based inference is different from those because it neither needs a likelihood nor a score based on a likelihood. It just needs knowing what is your joint probability. In principle, knowing a joint probability means I know a simulator that can simulate from parameters how my observations should look like. So this makes it a bit different from the other methods. Also some kind of a black box, but we'll get to that. All right. Now, before we go towards simulation-based inference, are there questions? Okay. Then I continue. So, as I said, what we can do is we can approach this problem just by simulations. So if we can sample from our joint probability density by running any simulator, whatever that might be, we can just approximate the posterior by rejection. So as I told you, you have the option of writing a joint probability as this product of prior times this marginal probability density, which is in this case the likelihood. Now, if I know the likelihood and my prior, I can do that and I can sample from it. So let's have a very simple example. That is a toy experiment here, or a toy example, and this is a simple counting experiment. A counting experiment like the following, where you have a certain process, a background process that is that is a Poisson process, and also your signal that is a Poisson process, and they can both happen with a certain magnitude. What is a Poisson process? Well, a Poisson process is any process where you can observe the, well, existence of an event, but you cannot really say that no event has happened. So, for example, a Poisson process is the occurrence of a lightning in a thunderstorm. You can say, you can count the lightning events in a thunderstorm, but you cannot say that no lightning has happened. So there is an underlying probability or a mean expectation value for how many lightnings you should expect in a thunderstorm, but you cannot say at what exact moment they should occur. So this is a Poisson process. Hmm. Now let's say this is a more advanced Poisson process like the decay of an atomic nucleus. Let's say you have uranium and this will decay. And this uranium is inside some rock that for some reason also contains another radioactive material, let's say thorium, which will also radioactively decay. You are interested though in the uranium decaying, so this is your signal. This will decay with a certain rate. You know when it decays, but you cannot say when it does not decay. So it's a Poisson process. And the strength of your decay is a certain, well, amplitude. Let's say you don't know that, but it's a value from 0 to 10. So you don't know how much uranium there is in the thing. And then you have also this thorium, which is also radioactive. And this might decay on a constant rate. You know better because you previously measured your rock and how much thorium there is. So it's only between 0 and 2, but it's a constant background to this decay. Now, so the overall process is that both isotopes or nuclei will decay, and this is a combined Poisson process. And the only thing you measure is, well, is there some radioactive decay happening in my rock or not? So it's the sum of both, and this is our count rate C. Now, what you can do is you can observe this rock and measure the count rate. So let's say you do this as a time series for, let's say you measure 1 day, and in 1 day you get a certain number of counts, and you do this repeatedly over many days, and you get this particular statistics. Now, you can simulate this with your prior belief that my signal component is kind of between 0 and 10. Okay, and this will give you as a simulation also this kind of curve. Let's say it like this. Now then, fine. You have this expected behavior of your model, and then you want to know for one particular observed target measurement where you measured, for instance, 3 counts a day. What is the probability of my strength of or presence of uranium in that rock given that particular observation? So what you do is, given your model, you just slice through this and you just track down for all combinations of the expected signal strength Z, what is the signal I would expect? So this plot here on the right is exactly the horizontal line through the plot on the left, which gives you very easily the approximate posterior because you condition your joint probability on the fact that you observed exactly 3 counts. And you do this in a particular way. So as you see here, I plot only the dependence on the expected signal set Z. I kind of marginalize over the existence of the background B. So this is implicitly in this particular simulation, but I only track the dependence on Z. And this is how you can get a marginal, a posterior distribution for the parameter Z of the signal alone. Okay, so basically it tells you, well, the most likely parameter that my signal has is kind of around 2.5. And doing this is the very simplest approach to a simulation-based inference. I just write here again what is the explanation of this previous plot. So it's basically just what I said. And this leads to the so-called ABC algorithm. So this approximate Bayesian computation. which is, in some sense, a fancy form of what we've just seen in this toy example. However, this is not as simple as before, because if you go back before, this was a problem that basically depends on two parameters where one has been marginalized over in the first place, producing counts. Reality is that your typical model will not just contain two parameters, and also your observation space will not just be one quantity that is one-dimensional, but it will be multidimensional. Let's say if you observe the sky, what you will get by observing the sky with a telescope is an image of the sky. If it's in the optical range of light, you will get just a picture of how the sky looks like. Now here, that's a much more complicated target space, and just plotting what I just did before is not as easy, even if you don't have too many parameters. So this will be a high-dimensional parameter space. And how do you do this? Well, it's very hard. Uh, what you want to do is you want to compress your data. And you've heard about compression of data quite a lot in the previous lectures. And what compression basically is producing a low-dimensional summary statistics of your target input. And your summary statistics is just there to reduce the dimensionality. So let's say you have a certain summary statistics that reduces the dimensionality to a one-dimensional object. Then you can play the same game again. You apply this and you simulate your observations, apply whatever this summary statistic does to reduce the dimensionality, and you get the same two-dimensional plot on your parameter if it's a one-dimensional problem, and the summary statistic of the observations. And you have again this dependence on as a joint probability distribution. Now, what you do here in this approximate Bayesian computation is exactly this. You have a certain target observation x0, which gives you a certain value for your summary statistic. So you go into this plot and you draw this horizontal line where the observation lies. And then, because it might be very hard to populate points exactly lying at that observation, because this is very hard to do, you have to take samples in a certain distance around this observation. So you define a certain distance metric in this space, and you keep all samples that are within a certain epsilon around your target observation. So this particular region here. Then you sum, um, of course, these points to form a one-dimensional distribution, which gives you this approximate posterior for the parameter. When you can do this, this is very simple to do. However, there are some, well, things to keep in mind. When you do this, to get the posterior, you always need to take into account that you have the summary statistic and this distance metric that defines you a certain region around your observation, because your observation space will probably be sparse in your simulation space because you cannot afford so many simulations. And well, in principle, the correct posterior distribution will be achieved if you let this epsilon go to zero. So what you want to design is that this is a well-behaved process, and in reality, you cannot really achieve this. So whenever you do an ABC inference of your posterior, this will be a conservative approach. So in most of the cases, your assumed or derived posterior will be a bit wider than it can optimally be, because you have taken a certain region around your observation. And well, just as a certain computer science or easy to imagine code-like structure. How you do this is what you have is your target observation. You have a prior of your parameter, and you have the simulator that can produce observations from these parameters. And given your tolerance for this metric and the number of observations you can afford. What you do is you simulate n times from your simulator, depending on how much capacity you have on your system. You store these simulations by sampling from these prior distributions, different parameters. You plug them into your model. Your model spits out a certain observation. Then you keep this, and in the next step, you ask, okay, I have my summary statistic that I now apply to this generated observation, and I have my target observation. And if the score that the summary statistic spits out is within the tolerance that you set, I keep this observation. Otherwise, I reject it, and I repeat for as many observations I want to have. And then in the end, it gives you a set of observations that are within the space that would describe your observation. So that's pretty straightforward, but there are these limitations. So it depends very much on your handcrafted summary statistic. And your summary statistic will probably not be optimal because you will have to sacrifice some information that is in the data that you could use that gives you a better handle to get narrow posterior distributions for your parameters. Well, and in practice, this sufficiency is very hard to guarantee. Then, yeah, your simulation might just be very expensive, and your simulation, they just grow with the number of parameters that you inject and then the dimensions of your output target data. So you might be limited there. Then this choice of epsilon is kind of also, yeah, magic. And you have to tune it such that you have still an accurate result. Um, but if you have it too narrow, you have a low acceptance rate, and you have to simulate so many times that this algorithm will never converge to anything useful. And if it's too large, you just retain too many different simulations that look not really like the actual observation you made. And this doesn't help you at all. And this is also an important point. There's no amortization. What is amortization? Amortization is a feature that some machine learning algorithms for inference have, and that is you train it once, and then you can use it for any target observation you want, and you don't have to retrain. This is different here. So here, this is handcrafted for exactly one target observation, and there is no way that you could use any other observation you might have made to go through the same step again and to get a different result. So this is targeting one particular observation. And you have to redo simulations again if you want to change the observation. So that's a bit of limitation here. But it's a good method if it's applicable for the particular case. So this motivates a bit why you want to go to this simulation-based inference framework with neural networks. For the approximate Bayesian computation, you go to these handcrafted summary statistics. While if you put in their neural networks, you have this, and you've heard of this, these reduction schemes. And you might even kind of link this between the simulator and the inference so that you just learn the optimal compression scheme in between. So there's an end-to-end learning or training of your summary statistic. Of course, you can also use handcrafted summary statistics in this neural approach, but well, we'll come to this later. So then you have still the cursor dimensionality. Well, there it is that even in a high dimension regime, neural networks seem to perform okay, and they can even perform in a reasonable amount of time and reduce computation time by quite a lot. If you go to, for example, GPUs, that's fine. There is no need for tolerance in these neural simulation-based inference methods, and they typically are capable of doing this amortized inference, so being able to train it once and then use different observations and get different posteriors depending on what your observation is. So you can reuse training data and training results. And this comes in different flavors, in which we'll address in this lecture. They are all based on Bayes' theorem and different flavors of what you actually want to infer. The first flavor is very direct. So what we are interested in this inference scheme is inferring the posterior of parameters. So we can directly estimate this in neural posterior estimation. In some cases, you are interested in the actual likelihood of your problem that you might not know in the first place. So you can then, in this neural likelihood estimation approach, estimate the likelihood function and do whatever you want with it. Then you might even do this Monte Carlo sampling of the likelihood in the normal way with the inferred likelihood. And then the third case is neural ratio estimation, which infers the ratio of either the likelihood to the evidence or the posterior to prior ratio. This comes in handy for certain types of problems, and we'll discuss this also later. All right. Now, so this was the introduction. Before we go into the actual part about distributions and what neural network estimation is, are there any questions about this first part of about the precursor of simulation-based inference, this approximate Bayesian computation? Okay. If that's not the case, then let's go to the following problem. So we talked about the posterior distribution of parameters given an observation, which is the quantity you want to infer. Well, yes. So how do we do this? And how do we quantify the similarity of certain probability distributions mathematically? You've heard about this in the last lectures from Alex and Gabby. And there's one quantity that we can apply that is called the Kullback-Leibler divergence. And this Kullback-Leibler divergence measures the dissimilarity between two probability distributions, P and Q. It's defined in this way. It is basically the expectation value of the logarithm of the quotient of one probability over the other, weighted with one of the probability distributions. So this is just an information theory definition, but, and I repeat probably what you already know, a certain property or certain properties, that is, it is asymmetric. So evaluating it first P and then Q, or switching the role of these two distributions, does not give you the same result. And you can use this to your advantage later in different methods to infer optimal probability density distributions. However, if these probability densities are the same, then also this Kullback-Leibler divergence is equal to zero. So it is exactly zero if they are the same. And it is always greater than zero, which is valid for P and Q, no matter if you exchange rules. Well, this simply comes from the fact, this non-negativity of this divergence, that you can look at the general property of the logarithm, namely that it's a known feature of the logarithm that it is always smaller or equal to x minus 1. And well, then you can just look at what the definition is and you perform this kind of estimate of the integral, and then you see, fine, pretty much works. Um, okay, so this is the property of this particular measure. As I said, you can apply this forward and backward, or forward and reverse, using this asymmetry of its definition. And if you use it in a forward case, this is the mask covering case. So you measure basically how the Kullback-Leibler divergence measures how Q spreads out and how it covers the full region of your initial distribution P that you want to approximate. And this is the typically way that is used in this newer posterior estimation case. And then you have this reverse Kullback-Leibler divergence, which is sometimes called the mode-seeking case. Because here you are then looking at a Q that tends to concentrate on one or a few modes of P. So you rather want to look at P as some distribution that might even be multimodal, and then Q concentrates on some of them, approximating this. And this you can use in something called variational inference that we also talk about later. Okay. Oh, did I? Ah, yes. Sorry. I forgot what the figure is. Just to mention, there are other little measures that you can use to quantify the particular dissimilarity of distributions. There's something called the Jensen-Shannon divergence, which is a symmetrized form of this Kullback-Leibler divergence, as you see here. So you basically take as the test distribution the arithmetic mean of the two test distributions, and you test the arithmetic mean of the forward Kullback-Leibler divergence of this arithmetic or averaged probability with respect to P and Q. This gives you some advantage at some point and some not. And then there's something called the Fisher divergence. Just to mention it here, this one is a bit different because this is basically a score-based divergence measure based on the gradient of your log of the probability distribution. And here, these distributions don't even need to be normalized because this is really only depending on the score between these two approaches, these two distributions. And to just show you how this looks like, so in this example, I just visualize the two distributions we have. So let's say distribution P is here in blue, a normal distribution, a standard normal centered at 0 with a standard deviation of 1, while the distribution Q is another normal distribution but centered around 1 with a standard deviation of 2. Okay, so they are similar in some sense, but these three different divergence measures give you a different notion of how dissimilar they really are. So this Kullback-Leibler divergence in the forward case basically shows you this. So it shows you here, okay, here it's positive. Well, because it is positive here in this particular space because P is larger than Q, while here it's the other way around. Fine. And they are 0 exactly at the points where Q and P are identical. And this you see here in those crossing points. Then you have this Jensen-Shannon divergence, which is the symmetrized version and shown here as the dashed line. This thing is fully positive, even if you evaluate it only at different positions x. And this Fisher divergence gives you this particular score here as dotted lines. I said before that the Kullback-Leibler divergence is always positive, which is true if you take the full integral and you compute the expectation value. Of course, this here is the value plotted at certain positions of the probability density function. So of course that can be negative, but the overall measure is positive. Okay, so just to visualize what it does. And what you want is basically if you want that Q approximates the probability density P, that the Kullback-Leibler divergence shrinks. So you want that these peaks here, they shrink and they all tend towards zero. All right. Now, with that said, let's look into the different flavors of simulation-based inference and what we have. So, okay. Now, we have this neural posterior estimation. And what is the goal of neural posterior estimation? Well, the goal of neural posterior estimation is to train some density estimator to approximate the true posterior of the problem. We don't know the true posterior of the problem in the first place. But what we can do is we can say that we have a neural network that is here to parameterize this distribution. And what we want to train are the network weights. And this is what goes into the problem. So what is the best way to train your network to become a probability density distribution that approximates the true density of the probability, the posterior of your parameters? So what we can do is exactly using the Kullback-Leibler divergence. So we go into minimizing this particular object in this forward mode. So we say, given the definition, this quantity here, the integral over the parameters of the posterior of the problem using the Kullback-Leibler divergence, so the logarithm of the ratio of the true posterior and our posterior that we want to approximate. Or, given here, the expectation value of this quotient of the two probability densities weighted by the or averaged over the different realizations of our model. There's a problem. This is impossible to do because we simply don't know the posterior distribution. So there's no way we can actually sample from this posterior distribution. So this actually doesn't make any sense. However, there is a solution that you can apply once you have a simulator of your full problem. And this is to average this Kullback-Leibler divergence over simulated data samples. So, of course, you can draw or you can produce simulations if you have a certain simulator that simulates your observations. So what you do instead, since we cannot directly sample from the posterior to perform this average process, we can also average over the different observations we have. So if we go back, okay, we can also perform this expectation values of our Kullback-Leibler divergence over the different, well, target data sets, or no, sorry, data sets we observe. And if you see here, here we are only sampling from the posterior. Now, if we add in the same line a sample of sampling from theta comma x times the posterior and the evidence, this is exactly this conditional probability that can be rewritten as the joint probability. So what we actually gain is, instead of doing those two expectation values, we can just do one expectation value, but we do it as drawing from the joint probability density function, which is in that way simply simulating examples from our simulator that we have. And then we can evaluate this. So if you write this now just using the normal laws of the logarithm, you get two terms. You get this term here, which is the expectation value of the logarithm of this neural distribution, which is our approximate distribution that we want to find, and a term that is expectation value of, well, the correct posterior. We don't know this, so this is still a quantity we don't know. However, it also does not depend on the weights of the neural network. So during training, this particular piece in the loss function is constant. And we don't care about this. It's just a piece that would add a number to it. What we can, however, minimize here in the loss is this function, because this depends on the parameters of your neural network. So this is fine. This we can do. And as you see, it depends on the quantity that we parameterize ourselves. So this test function Q. And it depends on samples that we draw from our simulator that we have. And well, exactly. Now the question is, how do we do this? Well, we have it, but we want to apply this. Well, that's a tricky question, and Gabi in the last lecture introduced to you normalizing flows. And you can use them as these density estimators for this particular topic. So just to recall what it is, a normalizing flow is a transformation of a simple base distribution into a more complex one. In order to do this, you want this to be an invertible transformation and to be differentiable. And as this is a flow, the typical notion is that you do many of these operations on your base distribution. So not a single one, but many being composed. So if you start with one random variable and its probability distribution, let's say a standard normal distribution, you get this theta zero, and then you define this chain of these simple transformations from f1 to fk on those base samples that then lead you to the final theta k or x. Okay, so this is very simple to do. So basically, if you draw samples from a normal distribution, you just get these numbers as a list of numbers, and you apply this function to these numbers, and then you get the transformed variables. What is not so simple, though, is to say what is now the underlying probability density function of these parameters x. So that requires a bit of computation. So you do this via this change of variables formula. Let's do it here in this log case. So if you take the log, then this will basically be the log of your probability density of the initial one minus the sum over the log of the determinant of the Jacobian matrix of these parameters. And these are exactly the steps of the composition. So what you need to do is to take the Jacobian of your transformation and to determine the matrix that is associated with this for each of the single functions in your transformation. This is kind of a bit of bookkeeping, and here it is necessary or to stress the fact that you want to do this with functions that are invertible and differentiable. Differentiable, of course, because, well, that's the whole point of your approach. So you want to be able to determine this Jacobian, and you want it to be invertible, because otherwise it's very hard to map your parameters. And also, your derivative will look a bit jumpy and maybe not continuous. So this is something you do not want to have. Okay. Okay, so how do we do this? Now, in the following, I have an example of this, but this will take a while. So I talked a lot, and I think I first stop here before I go into the example, and I'll let you ask questions if there are any. Okay. So if that's not the case, then I would say we stop here for a break, the typical 30-minute break, and then we reconvene in, well, yeah. Well, let's be generous. Let's say in 30 minutes, so it's 3 p.m. If that's okay with you. All right. Seems to be the case. So yeah, I've closed my video, and then we reconvene at 3 p.m. Okay. I I hope everyone is back from the break so that we can finish the lecture about the first part of simulation-based inference. And before the break, we were discussing the way to, sorry, to define how to have a density estimator that we can use for neural posterior estimation, where, to remind you, the task was to approximate in the best possible way the correct or the optimal posterior distribution of my parameters given a certain target observation with, well, a description that comes from a neural network and that fulfills certain criteria. So in order to do this, we wanted to use neural normalizing flows. And these normalizing flows are a sequence of function compositions that are applied to a random variable that then lead to a more complex structure of said random variable. And in order to do this forward, this is very simple in terms of the random samples themselves, but to identify what is the the probability density function of the transformed samples, this is more involved and uses the change of variables formula shown here in their logarithmic form. And just as an example, I want to give in more detail what happens if you, for example, use an arctangent function for the first one and then the so-called sigmoid function as the second function in your transformation as a normalizing flow. We'll start from a random variable that is distributed as a standard normal. So, in order to do this, well, we have this two-step flow. First, the arctangent. The arctangent will map our, well, samples in a different space, namely in a space from minus pi half to pi half. And then the sigmoid function will transform this again and bring them into a different support, namely the sigmoid function of minus pi half and sigmoid of pi half. So these domains are basically smaller than what I was before. So this is a transformation that will bring your initial normally distributed variable, which is in principle defined between minus infinity and infinity, to an open interval on the real numbers of length pi. While then the sigmoid function will squeeze this even more. So the sigmoid function only takes on positive values, and you will get a squeezed version of this between, well, let's say, minus 0.1217 and 0.83. So what you also might just recall from these functions is that they are both strictly monotonic, meaning that they are bijective and you can invert them. So what we are doing here actually works. All right, so let's see how this works in detail. So what we need to do here is to compute first the forward of the first transformation. So we apply the arctangent to our theta 0 variable that is normally distributed. And we need the Jacobian. Well, the Jacobian of a one-dimensional function is nothing but the derivative. So we take the derivative of the arctangent, which is 1 over 1 plus x squared or theta 0 squared. And I give you these derivations because I don't want to do them by hand in order to avoid any computation mistake. And well, in this formula that we had before, we're using the log form of this. So what we need here is the log of the derivative, which is minus the log of 1 plus theta 0 squared. Now, what you see is that since the arctangent is a function that has two asymptotes, namely pi half and minus pi half, So anything of the original samples that is kind of largish will be compressed to follow or to attain values exactly at this asymptote. So this is why this squeeze of the tail of the normal distribution will happen. So this is something favorable, of course, if you have a certain posterior that you want to approximate that lives in a smaller space than your actual initial distribution will be. So this is one step that definitely needs to be in there in order to get a well-defined posterior distribution with this method. Now, then we apply this first step of the conversion, and this is this change of variables formula. So you get the log probability density of theta 1 by this difference here. And just to recall, we have to substitute, of course, our theta 0 with the inverse function. There it's important that this is a bijective function, so that you can take the inverse in that interval, which is, of course, the tangent of theta 1. And then you can plug this in to get a function that only depends on theta 1. So the original form for your normal distributed variable is, of course, the standard normal, which you see here, which is in principle 1 over the square root of 2 pi times e to the power of minus 1/2 of x squared, or theta 0 square. And this is just the version that happens if you plug in now the correct density with the variable theta 1. Yeah, so you can beautify this a bit with some trigonometric identities, and then you find that your actual density distribution for the first change is this function here, which resembles the original one, given some of the factors that appear, and especially this secant function to the power of 2, which is exactly this Jacobian um, density or measure that you got from computing here this derivative. So that comes into play there. All right, and then we perform the second step. This is the forward of applying the sigmoid function to the variable theta 1. Again, we need to compute the derivative here. The derivative of the sigmoid function is just here as a reminder how this is defined. Basically, it's just that, so not too hard to do. And you plug this in, again, into your log of the Jacobian, taking the absolute value. And then you derive at this, which will become, again, the measure you need to multiply your initial function with to account for the change of variables. And just to name it, since this function is kind of symmetric around a certain point, you will get, again, the symmetrization of your final output. And you will squeeze this again in because the sigmoid function has also two asymptotes. It asymptotes to 1 if its argument goes to infinity, and it asymptotes to 0 if it goes to minus infinity. So you have a bit of a squeeze also there. Right. Then, again, applying all of this, same computation as before. Now we have to express the original 1, so this tangent of theta 1 or theta 0 as the inverse of all of these. And the inverse of the sigmoid function is the so-called logit function, so that in the end, you get these two relations between the different variables in the steps. Of course, this here is doable analytically because these functions are defined analytically. For general functions, this might be much more harder to express. However, this is always defined at least once these functions are bijective. Okay. And then putting everything together, it becomes a bit involved. So we define some shorthand notation for brevity, which gives you then the final density distribution for theta 2, which still can be kind of expressed in this old Gaussian or standard normal distribution, well, given the fact that you have all of these different definitions of variables. And well, fine. So how does this look in reality if you do this? So I show you here the visualization of the different steps that have been taken. So on the left, you see the original distribution that we had. So the standard normal and here, and the smooth curve or profile is the actual probability density function, while the samples that I've drawn here are shown as an histogram. Then we go to the next, which is applying the first transformation. So this arctangent. What you do with the samples is you simply take these samples here in black and you apply the function, and then you get just the histogram of the new variables, while the smooth curve here is the analytically computed function, how it should look like, and you see it matches. And then lastly, you perform the second normalizing flow that compresses these samples even more. For the samples, it's simple. You just apply the transformation, but the density again follows what we computed analytically. So what we did here is having always this derivative in there, which is this Jacobian, which accounts for the changing volume. And you see that the volume changes because the normalization here of the density on the y-axis changes too. So you compress the initial mass of the normal function in a smaller interval, requiring you that if you integrate over the full space, you still need to retain 1. So of course, the value of the density function itself becomes larger, and you account for this via this measure you compute. What you also see is that this particular choice of normalizing flow allows you to start with a standard normal distribution, but then you manage to derive something that is actually multimodal. And this is an example, if you recall it from last lecture that Gabi has shown to you, with this two-moon example, that this is necessary. So if it happens that your posterior needs to be multimodal, you can do it. You can introduce multimodality from a starting point of a standard normal, but of course you always have this bridge. So it's kind of hard to get a disconnected part here between the different modes, but at least a multimodality is possible to achieve. Um, of course, this can be made more, I don't know, deep with adding more steps in the transformation. But for visualization purposes, this is the general structure or the general gist behind normalizing flows. All right. Well, what would you do? So you want to use this, however, with neural networks. And well, there are several ways in the literature how you can use normalizing flows in certain architectures. And just here, I list you 3 different ways how to do this. And we'll discuss this in more detail in the next lecture next week. But just to give it here already. So you have mostly methods that focus on reducing the computational weight you have to do, because you always have to compute these Jacobians. And the example we had before was quite simple in the sense that it was a one-dimensional distribution. Of course, you can have multivariate distributions, and you will need multivariate distributions because typically what you want to infer from your actual data is underpinned by a model that will not just depend on one parameter, but many parameters. So you start with a multivariate standard normal distribution, and then your Jacobian is an actual matrix and not just a derivative. So you do have to compute that, take a determinant. So there are a lot of steps that are numerically kind of heavy, and people are looking for methods that make this computationally more easy to do and to reduce computation time. So there are masked autoregressive flows where the Jacobian can be constructed such that it is a triangular Jacobian, meaning that you only populate your matrix on the diagonal and the subdiagonals below or above the diagonal of the matrix, while the other side is 0, which helps you in determining the determinant quite a lot. And as you see here, it saves you evaluations. Then there's something called inverse autoregressive flow that gives you a more faster sampling, but a slower density evaluation. So it's kind of the inverse what they do there, but it has also its perks. And then there are Neal spline flows, which is currently the standard for Neal posterior estimation, which is a bit different from the first two because here they use monotonic splines as transformations, while the first two generally only use affine transformations. Well, affine transformations are, simply put, linear transformations, many of them, and even many of them can give you some nonlinear output. But this neural spline flow is even using quadratic or cubic functions to do the different steps. And I'll explain a bit in the following slides what this means. Right. Of course. Well, what is always stated here is that you do these normalizing flows, now parameterizing this stuff as neural weights of neural network so that it becomes trainable in the setup of machine learning and the algorithms we have there. Fine. But the question is, well, how does this work? So let me first make this little detour to these so-called splines, just that you understand a bit what the gist behind there is. So maybe you can look here into the right picture, where in this plot you see a certain interval from minus b to b. What you want is, of course, a differentiable function and a bijective function. So what you do is you take this interval and you define k bins in this interval. And with these k bins, you get k plus 1 knots. Well, the knots are just the dots here. And these knots are then connected in each bin with a spline. And the spline is, in this case, this function g here, which is a rational quadratic segment. You could also use a cubic segment that has been used in the literature, but let's take this quadratic segment here, which is such that, well, the whole construction is monotonically increasing, differentiable, analytically invertible. So you have some boundary condition at each of these knots in order to guarantee that this quadratic or rational quadratic spline is actually monotonically increasing and gives you a well-defined derivative at all of these knots. So these are kind of conditions that have to be satisfied in the construction. Right, from this you can of course get the inverse. There's an analytic formula for this. If you look into this particular paper, there it's computed in the appendix. So this can be done. And you see here the derivative of this particular example. And you see the derivative exists, but the second derivative of the function, well, is not really well defined. But you don't need this. You only need that it is once differentiable. And you already see that there is a lot of variation in this. And this is kind of the type of complexity that people like for these density estimators, because then you can approximate even complicated posterior distributions. Right. What you also see here in these equations with these functions g, well, these a, b, c, d, e, and f are the parameters. And these parameters are trainable. So these become part of the machine learning training. Because the actual question is, the analytic example I gave you beforehand was just about analytic functions. If you plug this in into a machine learning algorithm, well, you don't train anything. This is just something that is doing a particular action without any flexibility. What you want, however, is to have neural flows. So you do exactly this. You let the parameters of your Bijective differentiable functions become part of the training and part of a neural network architecture. So this makes this then a neural normalizing flows, where each transformation is parameterized by neural network weights. So you do exactly this as before, but now what you actually train are the weights of a network that is associated with this transformation. Right. And exactly. It just needs to be such that, um, in principle, the parameters become the weights and biases of this neural network. And the hard constraints that you must impose on this particular problem are coming from the particular method of neural flows you're using. Like as we have seen with these spline flows, that you have these conditions for each knot that needs to be satisfied to have this invertible and existent Jacobian determinant. Okay, so typically what happens in these neural spline flows is that you split these parameters and you do something that is called an autoregressive model. And more about this next week. Because what you want is that the parameters that you have in your problem, and as we've seen before, you can decompose your joint posterior in a sequence or product of these conditional probabilities so that you can train, in principle, these normalizing flows such that their output only depends on a certain number of parameters that are, let's say, the k minus 1 parameters before the actual parameters you train on now. So you can have like a certain influence by the past, but no influence from the future in a series of parameters. And basically, this is what is done here. So you apply the network only to part of the parameter set for element-wise parameter list, but you just let go through the other um, parameters that are coming next to this parameter later. And that's basically how it's done. But as I said, we have a look at this autoregressive feature next week in more detail. Right. So as I said, what happens is then that in this neural spline flow or neural normalizing flows in general, you have this trainable network at each step that depends on network parameters with the additional insertion that typically the observation that you're training on will come also as an input into the network. So at each step here, you will, of course, also show to it or embed the compressed observation into the input for the neural network to learn on. That's a bit the hidden thing in this particular flow and training step. Right, but then it's in principle just the same. You train it on the output, and via this particular sequence, you learn what is the output, or should be the output posterior distribution. Okay, so if we recap, what do we learn in neural posterior estimation? Well, we learn from a given training data set that is the number of parameters and associated model or training sample um, features that we've created that are drawn from the joint posterior. Or like this, drawn from a prior and then conditioning your simulator on those parameters and then drawing from them the observation. So you train it on pairs that match simulation and parameters. Then, as we've seen before, what you want is to minimize the Kullback-Leitner divergence while averaging over these different, Monte Carlo simulations or just draws from your joint probability. Let's say you have n of those training data sets. And then you do exactly this. You perform the average over those, and you just learn them via this neural network, which gives you in this flow architecture basically a learning about these different weights and biases in your function that determine the derivative of these different flows and the input there. Okay, in principle, this is then just a normal training. So you simply put in all of this, you show the training data, it computes that, and as an output, you want to show it as labels the parameters. Okay, and then this goes the normal training way, so there's nothing deep within that. It's just that your neural network is part of the normalizing flow. Okay, as I said, this requires the forward sample that you've drawn from your joint likelihood distribution, and you need a valid density estimator that is in this case described by these normalizing flows. And after training, well, you can evaluate this for any target observation you want. Why? Well, because your posterior distribution has been trained on the full model, so on the full model space that your simulator can produce. This is a reason why then, eventually, once you know the general posterior distribution conditioned on all available simulations that you could produce, given your model, you can then get one for your specific target observation. So you have this amortization feature. Okay, right. Other questions about this particular structure of neural posterior estimation? Okay. If not, then yeah, no, it's the same as we had before. Then let me comment just very briefly on something you could also do. Mm, Because I mentioned you could also use this reverse Kullback-Leibler divergence to estimate something. And then this goes along the lines of variational inference. So here you want to find the variational posterior that, again, given a target observation x0, gives you the posterior of your parameters theta, and that approximates the real posterior. But this time using the reverse Kullback-Leibler divergence, which requires you to perform an average or the expectation value drawing from your actual variational posterior. Again, we cannot evaluate this posterior, the true posterior directly, because we don't have access to it. That's the thing we want to know. So the solution here in this variational approach is to substitute it via the Bayes theorem with the product of likelihood times prior divided by evidence, which then in the same Kullback-Leibler divergence gives you this expression here, which is the so-called elbow. I think the elbow has been introduced also by Gabi last week. So this particular object appears here. And what you then do is basically you maximize the elbow to do variational inference, which is in principle a kind of a very comparable object to doing neural posterior estimation, but just in reverse. In fact, as you see here, what you need for this is a likelihood. And it is the likelihood P here of your parameters producing a target observation. So this means that the method can be done even without neural networks at all. So if you just parameterize a likelihood in some way with some parameters, you can do this. So this is a method that is basically a traditional method without the influence of neural networks. Of course, you can use them, but it's not necessary as long as you have defined a likelihood for the problem. Right. Mm, okay, that's what I said. So you have exactly here this likelihood term, then you have this prior term of the elbow, and something called the entropy. And the entropy comes from your test distribution that you want to, well, shape such that it best approximates the exact posterior you want to learn. And it kind of penalizes the overly narrow or low entropy distribution. So you kind of want something that's broad and not a super condensed posterior distribution. But as I said, this one is about evaluating a likelihood function. So it is a likelihood-based method and should be seen as such. Right. Yeah. Yeah. Okay. So this is just about training. I think it's not so important. There's just something how you do this in practice. Right. So to sum up this comparison, so the neural posterior estimation approach uses the forward Kullback-Leibler divergence, where you want to directly approximate your posterior, you don't know it, and you define a density estimator in terms of a neural network that is supposed to approximate this true posterior. While for variational inference, you do the reverse. You still have to now sample at this posterior that you create yourself. It might be a neural network based one or something that is very flexible but based on an analytic function. And you do it in a reverse Kullback-Leibler approach by getting the modes of the posterior, of the true underlying posterior right. Neural posterior estimation does not require any likelihood, while the variational inference approach does. Also, variational inference is not amortized because here again, you need the likelihood evaluated for the real observation that you have, while neural posterior estimation is amortized and you can reuse a trained network to infer any observation you might have. The parameters here are for neural posterior estimation drawn from the prior that you define, but for the variational inference, it is the variational posterior. So this is kind of a circular thing you're doing. Marginal inference is kind of trivial for this because technically in the posterior estimation, you can just say, I only train my parameters or the parameters of interest, and I completely forget about any nuisance parameters in the problem. So I can reduce the size of my parameters for which I want a posterior and effectively just marginalize over the rest. This works very well there. However, for variational inference, it does not. So there you explicitly must integrate these out and take this into account because this is part of the likelihood that you need to evaluate. Also, if you do this in variational inference and integrating them out, kind of completely erases correlations that might there between the parameters that you marginalized over, which is also not the case for neural posterior estimation. There, even if you marginalize over the parameters that you don't care about, you still retain their correlation, kind of implicitly, because you implicitly learn the likelihood, because you train on the full joint and the full simulation. All right. Okay. Which brings me very briefly to the next flavor of simulation-based inference. This is neural likelihood estimation. Well, neural likelihood estimation is now estimating the likelihood density. So exactly this quantity, the marginal of the joint, integrating out the impact of, sorry, marginalizing conditioning on the parameters. Right. All right. So, in principle, it doesn't really change. The only thing that changes is what your network is describing. While for neural posterior estimation, this neural network architecture was describing a posterior, it now becomes a likelihood. However, you can still use specialized architectures like normalizing flows to learn a likelihood function because intrinsically they are not so different. There's still a function of many variables, so nothing changes with that respect. So it's just the interpretation that changes of what you're learning. Um, However, this is, well, probably a bit easier, or yeah, it's a matter of what you want. When to use neural posterior estimation or likelihood estimation. Of course, for some particular tasks, you're actually interested in the likelihood itself, especially when the parameter space is high dimensional. You would rather do a neural likelihood estimation because then you might even use methods like Monte Carlo Markov chains to then sample this likelihood function or nested sampling. So some traditional methods, once you know the likelihood. Um, well, if the data itself is dimensional, probably use neural posterior estimation because, well, there it is easier to put in between also a network that compresses your high dimensional data with a summary statistic, and you learn it on top of the weights that the normalizing flow needs to learn to perform this transformation to the posterior. Um, while neural likelihood estimation is also not such a bad idea if, for example, you have multiple observations that go into it, because this you can use and this would easily factor in. Because you only condition here on the parameters, this naturally can include the fact that you have different observations that all underlie the same parameter set. So this might be an interesting application there. But then conceptually, nothing really changes. This is a bit different regarding the third type of estimation or flavor of simulation-based inference, which is called neoration estimation. So here, as I said in the beginning, is that you define a different quantity that you want to approximate with a neural network. And this is this likelihood to evidence ratio or posterior to prior ratio or joint to marginal ratio. Why is it called like that? Because it's basically rewriting Bayes' theorem. So if you look here, you have here in the numerator the posterior. And if you just take these two equations, you can rearrange it, bring this one here on the left side, and then you just have Bayes' theorem. And in this form, you see, by, well, also decomposing this conditioned probability into its actual definition, bringing out the joint probability, that this is the ratio of the joint probability density to the marginal probability density. Or expressed in different terms, this is the ratio of samples that are jointly drawn, so where your parameters produce exactly the observation that you see, while here in the denominator, parameters and observation data sets do not match. I can draw them independently of each other. And this is exactly what you want to use here. So you want to recast the estimate of this ratio as a binary classification task. Why do you want to do this? Because you can exactly do this. You can ask your neural network to distinguish two cases or two classes. Simulations and parameters match each other. So they come from the joint probability. They are drawn from the joint probability density versus class 2, which is data and parameter come from marginal posterior distributions. Okay, and in principle, you don't need to do this. You can just take your existing training data set and shuffle the actual data samples you created with the parameters and detach the meaning of labels and or parameters and data. So you even don't need to generate data twice. You can generate this once. And the only thing you need to do is to train an optimal classifier. So the optimal classifier is, or binary classification is something neural networks can do very well. They can very well distinguish between two classes as a classifier, and you can even derive from analytic principles what the optimal base optimal classifier should be, which is exactly this quantity here, which is the yeah this ratio here, which if you rewrite this can be expressed as the sigmoid function of the log of this ratio here with a bit of manipulation. So this is exactly what we use here. Or to make it more visual, how do you do this? Well, if you have any forward simulator which produces pairs drawn from a from a joint probability density function, x and theta, tuples, then we can train a classifier to tell us whether we are in a joint sample or a given set looks like a joint sample where these data points match with the parameters that label the data sets. So if you simulate pictures and you label them with parameters being, well, the labels for the image, then they match. Or if this tuple of pairs rather looks like a marginal sample where images and labels are scrambled. And that's it. Then you train with this exactly a classifier that gives you the sigmoid of the log of this ratio, and you can invert this to get back the ratio and eventually the posterior distribution. Right. Now, this is exactly what you do in terms of the loss function of neural ratio estimation. You want the optimal binary cross entropy to be minimized, which would give you the best classifier. So what you do is basically you minimize the loss here, which is the shared or the cross entropy between the target data set. If you do this, and if you minimize the cross entropy, you're minimizing the quantity that states that here in this particular space of your full sample, class 1 and class 2 look alike. So you want to minimize this region where they still have this look-alike feature. And this is nothing but this integral equation and this classifier d phi here is a neural network, where phi again refers to the weights of the neural network. And exactly, this gives you this particular ratio as the optimal output, which you can then recover by rearranging these quantities that you get with the formally applied analytic rules. And in principle, since this is just a network that is supposed to classify, the network architecture can be rather simple. So it is just an unconstrained network that can be a multi-layer perceptron, or as you sometimes call it, a feed-forward network, a residual network, but there's actually no complicated structure you need for this. So it can be as simple as you like, as long as there's some expressivity in the network to perform the classification task. However, of course, if your input data is high dimensional, you would like to have a summary statistic in between. So of course, you can define your network that first you have, let's say, a hat network that compresses your input data and then leads the output into this simple network that does the binary classification task. So you can make this a bit more complex because you need a summary statistic. Right. Um, exactly. Okay, so this is basically just the analytic derivation, why this works in this case and why you get the correct shape as a classifier that is working optimally. You can go through it later. It's not so important here. Okay, so if we compare these three methods of simulation-based inference with each other, what we have is that for nil posterior estimation and nil likelihood estimation, we learn with the network the actual posterior or the actual likelihood function, while for the neural ratio estimation, we learn the posterior to prior ratio, so a different object. The loss we need to train is, for the first two cases, this negative log probability that we train, while it's just the binary cross entropy for a classification problem for neural ratio estimation. The network for neural posterior estimation and neural likelihood estimation are normalizing flows normally, while for NRE, it's simpler. It can be a feed-forward network or residual network. You also need to normalize your network for neural posterior and neural likelihood estimation, but normalizing flows can do this, while this is not necessary for neural ratio estimation. The posterior sampling, well, for neural posterior estimation, this is direct. You just get the posterior. For neural likelihood estimation, as I said, you need to do this MCMC run to get your actual points, or you do a variational inference even there. The same is true for neural ratio estimation. You either do that or you reweigh your samples because you have a prior and you can just rearrange the formula. So that also works. So just the performance here, you see that the inference is very fast for neural posterior estimation, but can take seconds to minutes for neural likelihood and neural ratio estimation. On high dimensional data, what you would like to use is either neural posterior estimation or neural likelihood estimation, while it's a bit harder for neural likelihood estimation. However, if you have multiple observations, this is a bit harder for neural posterior estimation. There you have to retrain. So it's not so easy to combine observations of of the same thing, but from different experiments, different instruments whatsoever, while this is easier for neural likelihood and neural ratio estimation. However, this had nothing to do with this amortization. This is rather about the model being applied to different observations, where the model is the same, but you just produce outputs for different instruments, observation campaigns. Because amortization works for all three of those, in contrast to relational inference, for example. All right. Yes. Before I go through the last slides for this lecture, are there any questions about these three types of simulation-based inference? Okay. Then I will finish with a few adjacent topics and remarks. This is first about this data compression, because it often happens that your simulator produces data that is very high dimensional. Let's talk about images or whatever. Images can be produced by astronomical observations, by telescopes that are very high dimensional, but also simulations themselves. Like if you're looking at cosmological simulations of n-body codes, they produce very big simulations, even three-dimensional cubes that themselves are high dimensional. So what you then need is to compress the data, but still preserve information. So what you can do is, and what people have done in the past, even with this approximate Bayesian computation scheme, is to use handcrafted summaries. They are domain specific and they are interpretable. Just one example, as I've spoken about cosmology, what you could use is if you have a simulation of the large-scale structure of the universe, so basically the density of matter in the universe in a certain snapshot, then you can use the matter power spectrum, so the two-point correlation function of different points in your density field as a handcrafted summary statistic. This is physically motivated. It compresses your data, but it erases information. It works. It has pros and cons. But if you want to do, for example, a traditional approach with a likelihood-based method, this is something you typically use. Then you can also use something that is more information theoretically motivated with existing compression schemes that are motivated by information theory, or you do something that is end-to-end neural. So you have a neural network also parameterizing your summary statistic, which you don't care about at all. You just ask network, please optimize your network parameters such that I retain a lot of information from my input and I learn the most informative features. Of course, this can work, but there is a certain intuition required by you to use the best network architecture that is capable of retaining the features of your data that then can give you information. So this connects also to the previous lectures about how data compression with neural networks should work. Right. And yeah, so neural likelihood estimation is a beast. So if you try to learn the likelihood and do end-to-end summary statistics learning, this is complicated and it might just fail. So neural likelihood estimation of the three is the one that is the most finicky, but it can be useful in some cases. Then, again, I want to highlight the fact that simulation-based inference and this implicit likelihood method is advantageous in a sense that you can perform marginal inference. Because what you do basically is you train on draws of the joint sample. Here you can be as expressive and parametric as you want. You can include parameters of interest that directly relate to parameters of your model, biological parameters of your biological system, dynamical variables in your chemical process, or your parameters that play a part in your physics model, and some nuisance parameters. That might be parameters that come from your tabletop experiment because you have systematic uncertainties. You can model all of this. You can model all of their effects. You can simulate from the full joint, including the actual interesting parameters and the nuisance parameters. And then when training your neural network, you actually only train it or show to the training in this loss the parameters of interest. So you just marginalize over these parameters that you don't care about, the nuisance parameters, effectively by passing them via the created data sets to the network so that it still learns they exist, but you don't infer them. So the network sees that it sees that they have an effect, but you don't relate this effect to any parameter the network needs to learn. And this gives you a handle on scaling down the complexity of what your network needs to learn and your posterior distribution while still retaining the full covariance of all the parameters and all the complexity. So in a sense, you can go full crazy and only infer what you want. So this is a very nice advantage here. However, don't go too crazy because if your model can predict whatever you want, it's not a good model in the first place. So again, caution is necessary. Right. And yeah, basically, This is just a slide telling you that neural ratio estimation is something that can be interpreted in an energy-based way that defines a Monte Carlo method in terms of some physics model that is basically underlying some Hamiltonian, and you have a certain way of simulating things. So this is more for the particular special interest. Right. Um, Lastly, again, to highlight and to emphasize it, amortization. What is not doing amortization is all the traditional methods that use a likelihood. Monte Carlo, Markov chains, nested sampling, variational inference, all are based on an observation, a target observation. And everything you do in terms of finding the posterior is depending on this target observation. There's no way to infer the same parameters for a different target observation. So you have to rerun the whole thing again. While for simulation-based inference, it's different. They all know about the full model, the full simulation space, and you can just show to them new observations. And what it also allows you is to perform, well, coverage statistics, which we'll talk about in the next lecture next week, which is a way to make sure that what you are doing there in terms of posteriors is what you want and that fulfills some quality criteria. Okay, and just to summarize today's lecture, so we've learned about Bayesian inference and how it connects to what we do in the sciences, the life sciences, the physical sciences in terms of the inverse problem. That is not only inventing models for the sake of inventing models, but also to test our models against reality because our science is grounded in reality and deriving from reality constraints and, well, constraints on our parameters of the model or excluding our model. We've seen that one very simple way to implement this is approximate Bayesian computation that works if you have enough computation power and you have a good summary statistic to reduce high-dimensional data. Then we have discussed different posterior distribution and ways to measure their differences, also connecting with previous lectures. That is most importantly the Kullback-Leibler divergence that is used here as a mathematical tool to then train the three flavors of simulation-based inference, nil posterior estimation, very directly measure the posterior while having a network parameterized as a normalizing flow, or you learn in your likelihood estimation directly the likelihood of your data given the parameters, again with normalizing flows, or you perform neural ratio estimation, which gives you the posterior weighted by the prior, where you only solve a binary classification task, which is easier or not as heavy on the machine learning part as the other two. The key advantage of this neural way of doing Bayesian inference is using amortization, marginal inference, and data compression that can be done in one go while optimizing neural network parameters. Right. And just to stop here, so give you the references where you can have more information about this and what we will cover next week. That is how you do a sequential simulation-based inference. That is prior truncation, how you diagnose and validate the results of your inference, what are good practices, and a practical workflow to do this, and looking at some software that would produce some of these results on simple tutorials that give you a hint on how this is done in practice. All right. Right, so this was the first lecture on this topic. If you have questions, please, I'm happy to answer them. Okay. So, yeah, if you're happy without questions, thank you for the attention, and we reconvene next week at 12:15 for the second class of the topic, and I see you next weekend. Have a nice weekend.
Bye. Thank you.
Bye.
Bye, everyone.